Unit 6 is on correlation, regression, and association. Specifically, Section 10.1 is on correlation. And correlation is defined as the values of one variable are somehow associated with the values of the other variable. These variables are paired data, or we can also refer to them as bivariate data. A linear correlation, specifically, is a set of paired data that is correlated. When graphed, the plotted points form a pattern that can be approximated by a straight line, and that forms the basis of this, for the most part, for this entire unit. It is wise to use a scatter plot, though, to explore paired data visually to see what is impacting the correlation. And we can interpret the scatter plots in 4 different ways, depending on what we could see. Such as letter A here, we have a correlation coefficient of 0.859. This is a positive value, and we could see that it has a distinct straight line linear pattern. I mean, some of the points are further-ish away, but for the most part they follow a straight line. It's positive since it increases from left to right, and as the x values increase, so does the y, since again it increases from left to right. The letter B here is, for example, the second one, also a distinct straight line linear relationship. This one's closer together, which is why this has a correlation coefficient of negative, since the slope is negative here, negative 0.971. And it's negative since as the x values increase, the y values decrease. And you can also think of it as decreasing from left to right. Letter C is this third one, which is no distinct pattern suggests no correlation, right? Well, for one thing, it has a very low correlation coefficient of 0.074. But it's also because these points are scattered all over the place. You could draw any number of lines inside of here, but none of them are going to really fit the data well at all. Letter D here is a nonlinear, which just refers to not a straight line, but it is indeed correlated, right? You can see the type of graph here. This appears to be a quadratic relationship, as opposed to a linear relationship. It does give a correlation coefficient of 0.330. Do note this correlation coefficient in relation to this other one, right? Although we could say both of these are not linear relationships, we could still form a line instead of this one, and it won't fit the data that well, but we could still form a line in it. This one you can't form a line at all. So even though this correlation coefficient is, again, 0.3, it's very weak, but the fact that we have a correlation of 0.330 means we would have to look at the scatter plot to ultimately determine that it is non-linear. We can measure the strength of the linear correlation through that linear correlation coefficient, which we just denote with an R. It measures the strength of the linear correlation between the paired quantitative x values and y values in a sample. We could also call it the Pearson product moment correlation coefficient due to the fact that it was first found by Carl Pearson, born in 1857 and died in 1936. The population correlation coefficient is the Greek symbol rho, kind of looks like a P. Only not really a P. It's that Greek symbol rho. But whenever we're talking about these, we usually use the sample correlation coefficient, which would be R. To actually compute this, and as you can tell, it has a very scary looking equation, I know, but that's what it is. To calculate this, we would first need the requirements for drawing conclusions, where the sample of paired x, y data is a simple random sample of quantitative data Visual examination of the scatter plot confirms that the points are in an approximate straight line pattern, and any outliers must be removed if they are known to be errors. And the effects of any other outliers should be considered by calculating the correlation coefficient with and without the outliers included, to see how much of an impact it actually has, if any. The second and third requirements down here. These are a simplified version of checking for a bivariate normal distribution, just without that fancy schmancy terminology. To actually calculate it, if we wanted to do it by hand, I have three different forms of it. N times the sum of x times y minus the sum of x times the sum of y, divided by the square root of n times the sum of x squared minus the sum of x squared times the square root of n times the sum of y squared minus the sum of y squared. So the same thing as we're adding up the product of the z-scores of the x values and the z-scores of the y values, divided by n minus 1. That's the same thing as the sample standard deviation of x, y, so sample standard deviation of x times y, divided by the sample standard deviation of xx, meaning multiplying x by itself, times the square root of the sample standard deviation of yy, again meaning multiplying y by itself. But as you can tell by the fact that this is such a complex looking calculation, SAS could do this for us. But we would round this to we would round that correlation coefficient to 3 decimal points as needed. The p-value, which we could also get in SAS, if it's less than or equal to alpha, we could support the claim of a linear correlation, and if it's greater than alpha, it does not support the claim of a linear correlation. We could also use the table A6 in the textbook as well to get the same decisions when we take the absolute value of the correlation coefficient. If the absolute value of that correlation coefficient is greater than or equal to the alpha, greater than or equal to, the critical value, then we support a claim of linear correlation. Otherwise, if it's less than, the absolute value of R is less than the critical value, then we do not support that claim of a linear correlation. The linear correlation coefficient must be between -1 and +1 inclusive. If all values of either variable are converted to a different scale, the correlation coefficient does not change. The choice of x and y does not impact the value of the correlation coefficient. The correlation coefficient measures the strength of a linear relationship and not meant for nonlinear relationships. And the correlation coefficient is, as you could probably assume, sensitive to outliers. So for example, let's calculate the value of the correlation coefficient from this data set down here. So based on this value, is there sufficient evidence to support a claim that there's a linear correlation between pulse rates and white blood cell counts at the 5% level of significance? We have the data here and a scatter plot here. But I already put this data set into SAS. The file, not that, the data table looked at this, but I already put that here into SAS. We just need to build our code for it. So to do that, we need to type the following. We need proc core, since we're talking about correlation. You could also use the other correlation down here, but do note, as you could probably tell from the text box there, it does slightly change some of the values that you could potentially put in. So I'm just going to use core. Proc, C-O-R-R. I'm going to use data is equal to, I called this one work dot pulse. And I'm going to run it. Okay? And doing so will give us this correlation coefficient. Although it's in a special place, we'll see what that is in a second. Let me just move this over. Okay. So on here, we have our correlation coefficient specifically mentioned right here and right here. So in both of them, we obtain a linear correlation coefficient of, right over here, we obtain a linear correlation coefficient of about 0.405. Alright. And we could interpret that. And actually, yeah. We obtain this correlation coefficient of 0.405, which again shows that positive relationship, but do note how, well, number one, that's less than half, but we can tell it doesn't really reflect the data that well, since that's kind of low, and we have a couple of data points that don't look anything like a positive correlation, since they're just laying down here in the bottom right of this scatter plot. But based upon from this, we have that. We also obtain a p-value from this. We obtain a p-value from this. And that is due to right here, and right here, of 0.4988. And let me just very quickly write what that test actually is. This is a test of the null hypothesis, being that the correlation coefficient is equal to 1, and the alternative being that the correlation coefficient is not equal to 0. Alright, so null hypothesis, correlation coefficient is equal to 0. Alternative, correlation coefficient is not equal to 0. Or we could just say no correlation, no linear correlation, and a linear correlation. Just not written out in words. But we can write out what this actually means. And I'm going to type this just so it's easier to read. For this, the conclusion that we would make for this is, due to the fact that this p-value is 0.4988, that is nowhere near 5%. This would be at the 5% level of significance. We do not have sufficient evidence to support the conclusion of a linear correlation between pulse rates and white blood cell counts for all adult females. Now, mind you, there's only 5 data points here, so maybe a larger data set might tell us something different, but for the one that we have here, and that's what that tells us. Now, from this, we could interpret the explained variation from this correlation coefficient. This is despite finding if there is a linear correlation, there are other factors that may cause the expected value of y to not be the exact result that occurs. And we could find that by using the value of r squared. This is the proportion of the variation in y that is explained by the linear relationship between x and y. And that number has a special name that referred to as the correlation. The value of r squared there has a name as the coefficient of determination. And here we want to actually calculate that coefficient determination. So using that same data, what proportion of the variation in white blood cell counts can be explained by the variation in the pulse rates. That number is not on here. We'd have to actually do this one out. But we can easily calculate by just squaring the value. So r squared is going to take 0.405, and we are going to square it. And if we do that out, we get a value of about 0.164. Of course, it's rounded since we are using rounded values. But we could then interpret this. So we have an actual interpretation of what this value means. This will be, we conclude that 0.164, which is roughly 16% of the variation in white blood cell counts can be explained by the linear relationship between pulse rates and white blood cell counts. And because 16% can be explained, this then also means that 84% of the variation is unexplained, which is quite frankly not that good. But that's besides the point. A couple of common errors involving the correlation is assuming that correlation implies causation, just like before the phrase would be association does not imply causation. That's the same thing here. Correlation does not imply causation. When you assume that the correlation implies causation, both variables are impacted by looking variables, meaning variables that affect the variables being studied, but are not included in the study. Another error is using data based on averages. Averages suppresses individual variation and may inflate the correlation coefficient. And the third one is ignoring the possibility of a nonlinear relationship. And if there is no linear correlation, there may be a nonlinear correlation, which then in that case you might be able to fit some type of polynomial, such as a quadratic or a cubic, to the data set, depending of course. The formal hypothesis test, which we talked about before briefly, the null hypothesis is that there's no correlation, or that the population correlation coefficient is equal to 0. The alternative is that there is no significant correlation. The alternative of this is that there is a significant correlation. So I do not know why there's a no there. We know that there is a significant correlation if the alternative hypothesis was correct. That meaning that the population correlation coefficient rho is not 0. We can use the same test statistic r from before, or we could calculate the t-value r divided by the square root of 1 minus r squared over n minus 2 with n minus 2 degrees of freedom. But as I said before, it is located inside of this table that we get, which I highlighted there and down here. And using the paired pulse rates and white blood cell counts from example 1 to conduct a formal hypothesis test of the claim that there is a linear correlation between the two variables, using the 5% significance level and the p-value method for testing the hypothesis. As we had previously, the null hypothesis being that there is no correlation, so the population correlation coefficient is 0, and the alternative is that there is a correlation, so this is not equal to 0. And we obtained the p-value, as I said before, of 0.49 run that to 0.499. So due to that being very high, we are rejecting. We are failing to reject the null hypothesis. Again, as we saw before, that correlation coefficient was indeed pretty small to begin with. But we can write this as we conclude that there is not sufficient evidence to support the claim of a linear correlation between pulse rates and white blood cell counts of adult females. And then one last thing, for the most part, most of the hypotheses that we can make are generally two-tailed tests with regards to the test about the correlation coefficient. But we could still have a one-tailed test with a claim of a positive linear correlation or a claim of a negative linear correlation, meaning that the alternative for the positive would be that the correlation coefficient is greater than 0, or the alternative would be that the correlation coefficient is less than 0, which again summed up inside of this table down here. Let me know if you have any questions or concerns. Thank you.